All right. Okay, so last class we finished up and we actually proved that the volume of a solid ball is 4/3 pi r cubed, right? And that was pretty cool. So I thought I would continue with that idea. And on my way here, I was thinking, you know, there's this object that kind of looks like a cone, but you've kind of like cut the top of it off, right? Like a cone, but you cut the top off. Y'all see it there? Like a lampshade. Yeah, lampshade. We can do that. Okay. So let's say we have something like that. Let's say that somebody tells us how tall it is. Let's say someone tells us what this radius is, and they tell us what this radius is. Because there's kind of like two radii there. Do you see that? So let's call this r sub 1, and let's call this r sub 2. Is that fair? So on my way in here, I was thinking, there's got to be somewhere, and we could probably Google it, and probably come up like with get the volume formula for that. Well, let's see if we can't come up with it on our own. All right? So last class, what we did to find the volume of a sphere, or of a solid ball, was we looked at just the circle, right, in the first quadrant, and we wrapped it around the x-axis, right? Can you think of how we might be able to do something similar to get the volume of something like that? What? Huh? Two? I'm not sure I'm following you. I'm saying, let me rephrase the question. To get the volume of the sphere, we wrap this quarter circle around the x-axis. What could we wrap around the x-axis to get the volume of that? What would it be? What geometrically, how could we get it?
Like some sort of line angle?
Just a line,
yeah,
right? Just a line. Look, if I take this x and y axes, and I draw a line. Let's say, let's just start it here. For convenience, let's start it right here on the y-axis. Let's bring it down to a certain point here and just stop. If I wrap that around the x-axis, I'll get this shape sideways, right? Turn sideways, won't I? Okay, so I'm wondering if maybe we can come up with a formula that would give us the volume of this. Are you with me? I don't know what the formula is, okay? Like I don't have it memorized, so I'm hoping we're going to do this, and then we're going to get on Google, and we're going to try and find it, see if our answer matches, all right? So to do this, didn't we need to know the actual curve? Like we needed to like solve for y, and we said y was equal to like square root of r squared minus x squared. We did that last class for this. But for this, I'm actually going to need to know what the equation of this line is, right? What is the equation of that line? Now we know lines all look like y equals mx plus b, yes? But for this particular one, what is the function? What did you, I didn't hear you. Negative? Well, it has a negative slope, I agree. But what we have to assume here, like with this, the only thing we assumed was that the radius was r, right? For this circle. Here what we're assuming is that we're given a radius here, we're given a radius here, and we're given a height here, right?
Negative x plus h.
I think y'all are trying to get the equation of the line too fast here. Give me some more information. What's something else I could put on this graph that I know for sure? Like, do you know what that point is? What would that point be? It has an x and a y coordinate. Can you tell me what it is? Well, the x is 0, right? We've got that, yes. Okay, but what would the y have to be if we're going off of that picture over there?
The center of R2.
R2. It'd be R2.
Is that R2 or R1?
R1.
That's R1.
Yeah.
That's R1. So look, let me draw this sideways. Like that. We're basically wrapping that around the x-axis, right? We're wrapping this around the x-axis right there. So the distance from here to here is that distance, right? So the y coordinate there should be R1. Y'all with me? Okay. Now, what about the other point? So R2 here, because that's this distance. Okay, what about the x-coordinate? Do you know what the x-coordinate is? H. Just H. Look, H is this distance, right? So if I lay it sideways, it's a distance from here to here, isn't it? So that's H. Okay. If I have 2 points, can I find the equation of a line between 2 points? Yes, there's a formula that we have. It was y minus y1 equals m times x minus x1. This was what we called the point slope formula from way back when. So if I know a point on the graph, which do I have a point on the graph? I have 2 of them actually, but I only need 1 of them. And if I have a point on the graph and I have the slope, right, the slope, then I can give you the exact equation of that line. So as far as the point is concerned, let's call this x1, y1. Let's call this one x2, y2. I could have done it the other way around, but that's the way I'm going to do it. So I have x1, right? I have y1. All I need is the slope. So how can I get the slope of the line between 2 points? By definition, slope is rise over run, y2 minus y1 over x2 minus x1. That's a formula also from way back when, yes? Okay, so what is that for us in this problem? Our slope is r2 minus r1 over h minus 0, so that's just h, right? That's our slope. Now remember, r1, r2, and h are all constants, right? Those are all fixed numbers. The only thing that's variable in here is the x and the y coordinate, right? So I come here and I say y minus what was y1? r1 equals m, which is this. It's ugly, but, you know, it's life sometimes. Okay, h, and then x minus x1, which is 0. All right, now when I do this, x minus 0, that's just x, so it's this times x, right? And then I'm going to bring the r1 over to the other side. So I have y equals r2 minus r1 over h times x plus r1. This is the equation of that line. Y equals mx plus b. Okay? Now, you ready to wrap it around the x-axis? Find its volume? So what was the main thing that we took away from last class? I know I didn't get to go through a lot of examples, but let me just put it here from last class. We had that if you had a function on top f and a function on the bottom g, and we wanted to take a little rectangle in here, right? And I drew it over here on the side. Does this all look familiar? Yeah. And we wrap it around the x-axis like this. Okay, then that's going to create this washer. And we came up with the formula for that washer, and then we said we're going to add them all up, right? And at the end of all that, we came up with this formula. Pi integral a to b of the top function f of x, you remember what it is? Squared minus the bottom function g of x squared, all of that dx. So this was like this thing squared times pi times dx was the formula for a cylinder, that the volume of that was pi r squared times height. So it was kind of like this is the radius squared, that's pi, and then the height of this little washer was the dx. So you have to go back and look, but that's where it came from. So we were taking the big outside and subtracting the little inside. Okay? So according to that formula, I just need to look back at this and see where my top and bottom functions are, what they are. So we all agree that my top function here, this one right here, I don't know, I do not know what it is. I know what it is now, right? This is this one, right? And I'm going to call it f because it's the top one. So f of x, I know, is r2 minus r1 over hx plus r1. That's that one. Now, what is the bottom function? So imagine your rectangle, right? Where's it going to go to? All the way down to the x-axis, right? So this is that case where our function on the bottom is actually just y equals 0. Right, that's this. Right there. That's your g of x, it's on the bottom. And that's just the constant 0 function. Heads up. I don't think I'll hit you. I don't think I'll hit anyone over here. Oh, that's way off. Okay, what did you say? What? Huh? 0 what? Yeah? Were you saying something? This is 0, right? We're all good with that? Okay. So that's it. We're ready. Let's do it. We have, we didn't talk about where the integral is going to go from. So our rectangle is going to move this way, right? Through the region here. It's going to start here at 0, and it's going to end here at this x-coordinate, which is h. So our integral is going to go from 0 to h. So the volume of this rotated around the x-axis is going to be pi integral 0 to h, the top function squared. So let me do it this way. It's going to be that top function, which I'm going to write as r2 minus r1 over hx plus r1, all of that squared. That's our f of x squared, right? Minus that squared, 0. I'll just put it here just so that you can see all the pieces, all right? Now, at this point, I'm going to square that function, all right? And the reason why I'm not afraid to square it is because this is just a linear function in x, right? That's a number. Whatever it is, it's a number times x plus, that's just a number, right? A constant. So if I square it, I'm just going to do like foiling, right? Okay, so let me do the algebra of that over here. If I do R2 minus R1 over h times x plus R1 times itself, R2 minus R1 over h times x plus R1 again. When I do this to this, let's see what happens. The x's square, don't they? And that whole thing in front squares. So watch the way I write this. I'm going to write it R2 minus R1, that part gets squared. The bottom gets squared, h times h squared, and then the x gets squared. Now what about our middle term? It's going to be this times this, right? And then we're going to have another one of those. This times this, so 2 of those. So we have 2 of the R2 minus R1s over h times x. You follow? And then what's our last term? Plus r squared? R sub 1 squared? Okay, that's this thing expanded, right? Now I need to integrate that from 0 to h with a pi out front. So I'm just going to save myself some time. I'm going to integrate this, pi out here, 0 to h, and all of this is with respect to x. All right, let's integrate. The antiderivative of this might look horrific.
Wait, aren't you
What?
missing a piece? Because it's r sub 2 minus r sub 1 over h plus r sub 1.
Plus r sub 1.
Like when you...
Oh, times r sub 1. Yes, I'm sorry. Yes, I'm glad you pointed that out. That would have screwed everything up. When I go here to here, it's this times this. So there's 2 of those. I forgot to put the r1 next to the x. Right? Y'all see that? Good catch. So where should I put it? Just right here? Let's just put it right here. R sub 1 x. That. Yes? Everyone see that? Okay. All right. Integration. Like I said, this looks horrific, but really this is a number, right? This is just a constant, so I'm just going to bring it for the ride. When I take the antiderivative, all I have to do is integrate that. So this is going to be pi, and then I'm doing the antiderivative now, so it's all of that constant, r squared minus r2 minus r1 squared over, this is going to be 1/3 x cubed, right? So that 3, I'm going to put it here next to the h squared, x cubed. Okay? And then plus, Now the antiderivative just of x is 1/2 x squared, right? And that 1/2 is going to kill the 2. Yeah? So I'll have that r2 minus r1 all over h. I still have the r sub 1, and then x squared. And then I integrate this. This is just a constant, so r sub 1 squared times x. Right? Okay. And I'm evaluating this from where to where? 0 to h. All right, so I'm going now to go back into this and replace all my x's with h, right? And then all my x's with 0. So let's do the 0 one first, because I think you'll see what happens pretty easily. 0 goes in here, that's dead. Here, it's dead. Here, it's dead. So I'm not going to get any contribution from this right here. All it's going to be is what I get when I plug in h. So I have pi. All right. We have r2 minus r1 squared over 3h squared, but then I'm replacing x with h, so that's h cubed, right? Like that. And then plus r2 minus r1 over h times r1 times what? H squared. So replacing that x with h squared, or x squared with h squared. And then plus finally r sub 1 squared times h. And some pretty cool stuff's about to happen. This h squared is going to turn this into just h, right? This h is going to turn this into just h, isn't it? So they all have, every single term has an h, doesn't it? Every term has a single h in it. So I'm actually going to factor out an h at this point. So I'll put that right here. We get pi times h times r2 minus r1 squared over what? 3, and then plus r2 minus r1 times r1. That's this and this. The h's are gone. And then this one plus r1 squared. Do we agree? Now, I could probably go look for a formula right now, but I'm not going to yet, because I don't think the formula is going to look like that on the web if we go look for it. I think what we're going to need to do is get a common denominator between these and put them all together, because look, I'm going to have a lot of common terms in here that might cancel or combine. Do y'all see that? Like when I distribute this, I'm going to get an r1 squared there, right? And that's probably going to kill this one off when I'm done. Yeah? Yeah, let's just keep going. If you walked in a little late, we're trying to come up with a formula for this object, which has a radius down here of r1, a radius up here of r2, and a height here of h. And I believe this is called a frustum. Who said that? Yeah, it's frustum, right? You've heard that before? That's called a frustum. So we're trying to find the volume of a frustum. Or a lampshade, if you like. So we proceed. Okay, let's do this first. I kind of like the idea of distributing this through real quick, here to here, here to here. So if we do that, we get r2 times r1, right? And then minus r1 squared, but then this one is still plus r1 squared, right? So these two cancel, right? So I have pi times h, and then we've got this, I'll leave it for now, r2 minus r1 squared over 3, and then the only thing left over here is what? R2 times r1. I'll change the order. I'll do r1, r2. Doesn't matter which order I do that in. So that already is starting to look better, isn't it? And now to put those two together, to combine them, I'm going to need a common denominator, aren't I? So I'm going to make this over 3 and put a 3 in front of that. And so I get pi h, and then I think we can't avoid it anymore. We have to square that. So that's r2 squared minus 2 r1 r2, or you could say r2 r1, and then plus r1 squared. Agree? That's that. It's going to be over 3. But then we have plus the other numerator, r1, r2, like that, and all of them over 3, right? Okay. And does anything combine there? I guess we can put that and that together, right? I think we're there. I think it's clean enough for me to be happy. 1/3 pi h times r2 squared, what? Plus r1 r2 or r2 r1, however you want to say it, and then plus r1 squared. Right? Now the 3 on the bottom I just pulled out completely as a 1/3. Shall we check? I feel pretty good about it. Let's see. If it's wrong, we get the day off. Okay? Volume of a frustum. So they're using, yeah, there it is. They're using capital R. Stop doing that. Okay, can y'all see that? They're using capital R, we used R1, right? They're using little r, we used R2. And the formula is pi times h over 3, which is this. Yeah? Yes? Okay. So all I'm saying, I guess, with this is that if you're trying to find the volume of a solid, if you can somehow envision that solid as being something wrapped around the x-axis, you can generate your own formulas for them, right? Now, in my other class that I did yesterday, we actually did the volume of a cone. So it went all the way to the tip like that. And with this, all you need is r and the height. And the volume of that is 1/3 pi r squared h. But we did it exactly the same way. The only difference was there, the line there, what does the line there do? Yeah, it goes all the way to the x-axis. And that means this point is h0, which is a much cleaner point to work with. And this point right here is 0r. So it's this problem I did yesterday in my other class was a little bit easier to work through because the zero here instead of 2 different radii. Make sense? Okay. So, what are we going to do today? Take the day off. No, we can't. Sorry. All right. So, a quick recap of where we are. All right. When it comes to areas, if we have a function on top and we have a function on the bottom and we want to know the area, and this is between A and B, then we imagine putting in a rectangle like this. We find a formula for that rectangle, which is just the difference of the 2 functions, f minus g, and then the width, which is dx. And we add them up. So we have an infinite number of those rectangles. That's where the integral comes from. And then it's just f of x minus g of x dx. We good with that? Okay. Now we also talked about, well, what if your functions are not functions of x and instead they're functions of y? So what if they go like this? And then let's say you have another function, maybe does something crazy like that. So let's call this g, let's call this f right here. So to get the area there, what we do is we change our perspective a little bit, and instead of doing our rectangle going vertically, we do our rectangle going horizontally. And this changes a lot of things now, because now what we're looking at are these 2 points on our y-axis, which we called C and D. And the integral pretty much remains the same. We're going to add up all those rectangles. It's going to go from C to D. So now our rectangle is moving vertically, right? It's a horizontal rectangle that moves vertically up and down. And then it's going to be which function minus which function? The one on the right side minus the one on the left. So when I put f here, it's going to be f of y because it's a function of y now instead of x, and then g of y, and then dy because, well, our differential this way, the width of that rectangle is a change in y instead of a change in x. Okay, so we've got that so far, right? Then we start talking about volumes. And up to this point, if we have the same picture with f and with g, and we want to wrap this around the x-axis. Now, did I draw that little double arrow for y'all last time? Yes. Yeah? Okay, so if I'm wrapping this around the x-axis, I'm going to get a solid. And to do that, I wrap this rectangle around, and I get the washer and all that noise, right? We still are going to go integrate from A to B, because what we're doing is we're allowing our rectangle to move left and right between A and B. So we add them up from A to B, but because of the shape of the washer, right, we have to include a pi out here, right? We've got to put the first function, the top function, right? The top function squared minus the bottom function squared, and then dx. So this is all review of what we've done, right? So what if we have this picture and we want to wrap it, we want to find the volume wrapping it around the y-axis? What do you think is going to change? It's still going to be the same formula, right? We're still going to have pi. We're going to go, instead of A to B, we're going to go C to D. And instead of f of x, it's going to be f of y squared minus g of y squared dy. So exactly the same principle, all right? So I'm not going to go through and draw all the pictures of the washers being created. Just realize that when we take this picture and wrap it this way, our washers look like this now instead of, vertically, okay? All right, so I'm going to put that down. I'm continuing here with volumes. I'm going to draw another picture. So if we have this scenario, where that's f and that's g, and this time we're taking our rectangle this way and wrapping this around the y-axis, right? And we want to know the volume. C is here, D is here. It'll be pi integral C to D. Like you said, the f function, which is the function on the right side, squared minus the function on the left side, squared dy. All right, that's where we are, all right? We have not done an example of this yet, right? But can we extend to that idea without having to go through a whole formal breakdown of it? Y'all comfortable with that? Okay, before we move to the next step, let me just remind you. When we did the washer, when I introduced it last class, we said that washer, the way we're going to get the volume of that is we're going to imagine that washer without a hole cut out. We found the volume of that. Then we subtracted from that the volume of the piece we want to cut out, right? So we said that will be equal to the disk, right? The disk, the big disk minus the small disk. The big disk, we needed to know its radius, right? We needed to know the distance from here to here. And that was always the f function, because the f function was the top function, right? And then we needed to know the radius of the small one, and that was g, because g was always the bottom function. So back to here. When we wrap this around the x-axis, the big disk, that distance right there is what gave us the radius, right? And that's why we did squared, because pi r squared. Yes? Okay. And then the inner one. All right. Okay, let's move forward now. So what if we have a scenario like this? What if we have this picture, function here, f, this function g, but instead of wrapping this around the x-axis, I want to wrap it around some arbitrary horizontal line. So it doesn't have to be the x-axis anymore. So let's say I just come down here and I wrap it around this axis down here. I'm just going to make it up. There we go. There it is. So I want you to wrap it around that. So let's just first get the first thing out of the way. Will you have the same volume? If I take this and wrap it around the x-axis, right, is that going to give me the same volume as taking this and wrapping it around this axis? Yes? No? I'm hearing. Okay, so if I wrap this around the x-axis right here, if I wrap that, it might look something like, I mean, it's going to be terrible. It's really hard to draw this stuff by hand, but that's basically the shape of this wrapped around the x-axis. Here's my x-axis through there. I mean, on the inside, it's got some weird stuff happening, right? Yeah. But you know, I could put my arm through here. Yes, that's going to have a certain volume to it, isn't it? Right. That's that one. But if I take that and wrap it around this axis, now my shape looks like this. Like my axis is right here, right? My top edge is still here, right? Still that, but look, if I come all the way and wrap it down here, the bottom edge is now down here, isn't it? Yeah. So now it's like this huge solid instead. Do y'all see the difference? Those have to have different volumes, right? I mean, they do. They do. I mean, just think about how much material is inside of those two solid shapes. There's a lot more material in the big one than there is in the small one, right? So we're going to get a different answer. We should expect a different answer. My question is, how does the formula change? Because this formula won't work anymore. This only works when I wrap around the x-axis, because when we were saying what was the radius of that washer, we said f of x, right? And then squared. And the reason we did that is because our washer, that big disc, right? The center to here, we said was f, right? But that's because this was the x-axis. So the distance from the x-axis to the function is the radius. But here, the distance, when I take this rectangle and I wrap that around, let me wrap it around. Let me erase this. If I take that rectangle and I wrap that around, I get this huge washer, right? It's not the best washer, but I get this huge washer, right, that got wrapped around this line. And when I'm looking at the distance from here to here, it's no longer f, is it? So my radius has changed, and we need to account for that, all right? So the question is, how are we going to account for that? So let me show you how we're going to do it, all right? We're going to analyze this picture a little bit more. What we're going to be interested in is knowing what the distance is from here to here, right? That'll be, I don't know, how do we say it? That's the radius of, I had big one minus little one, right? So this distance from here to here is the radius of the bigger one, right? And what should we call that? I'm going to call that capital R radius O. For outer. That's the outer radius, okay? We're going to need to know what that is, aren't we? And then we're also going to need to know the distance from here to here, and that would be the radius on the smaller one, right? I'm going to call that capital R sub I for the inner radius. So the O here is for outer, the I here is for inner. With me? Okay. I might write R out, R in later, but I'm going to do R sub O and R sub I for now. So let's just think about what what that would be. Like for us in this picture, wouldn't the outer radius be this distance right here plus that distance right there? Yes? So if someone told me that this, just for the sake of explanation, let's say that this line went through -6 right there. Then what would be the distance from here to here? The distance. The distance would be 6, wouldn't it? And then you would have to add to that f of x. So the outer radius would be f of x plus 6. And then the inner radius would be 6 plus g of x. So it would be g of x plus 6, wouldn't it? Okay, so we're going to have to start to change our perspectives a little bit. When we wrap around the x-axis, it's just a formula. There's no thought involved, really. When we wrap around an axis other than the x-axis, we actually have to go and draw a picture. Well, I encourage you to draw a picture to get a real good, solid idea of what that outer and inner radius is. All right? So if we follow this kind of template, the volume of that wrapped around this axis would be something like pi integral. We'd still go from a to b. Okay, so a is here, b is here. Still go a to b. But instead of saying this squared, it would be what squared for us here? F of x plus 6, which is the outer radius, right? Squared. And then minus the inner radius, right? Squared. And then dx. That's kind of a more general formula now, isn't it? Like when we're back here, we're wrapping around the x-axis, what's the outer radius? Just f of x, right? What's the inner radius? Well, just g of x, because we're going around the x-axis. But in more general sense, it's just whatever that is, and we'll have to find it. It'll depend on the problem given to us, okay? Now this can get a little bit tricky, because just take into consideration this picture right here. We're going to do an example, don't worry, okay? What if I had this picture here? Getting tired of drawing this over and over. Okay, there, right? But let's say we wanted to wrap this around that up there. So let's look at our rectangle. Our rectangle's right here, right? And that gets wrapped around like this, doesn't it? Say again? Whatever, you get the idea, yes? G what? So G does have something to do with the outside. Yes, it does. But what is it? So let me label some stuff here. Wouldn't the distance from here to here, wouldn't that be RO? And wouldn't this one be RI? So imagine yourself, what I always like to do is imagine myself, when I'm trying to get a visual of what's going on here, I imagine myself standing on this dotted line, okay? This is my head, my feet are on the ground. So I'm sitting here, I'm standing on the dotted line. I'm looking out and I can see the rectangle laying on the ground. Okay, can you see that? I'm looking out, I'm seeing the rectangle laying on the ground. And I'm asking myself, if I were to get a tape measure and measure the distance from my feet to the edge, that's always my outer radius. And the distance from my feet to the inner edge is always the inner radius. So when I'm here, I'm standing here, right? And I'm looking out. And I'm saying, what's distance from my feet to the outer edge? That's the outer radius. What's my distance from my feet to the inner, right? Edge is here. Inner radius. Do y'all see that? Okay, so let me give you an actual value so you can kind of work with this again. Let's say that this value up here was 8. And remember, this is F up here and this is G down here. Then what is the distance from here to here? So the distance from here to here is 8, right? It's got to be smaller than 8. So the distance what's the distance from here to here? That's G, right? So 8 minus G. This R outer is 8, take away whatever G is. And then this one right here is 8, take away F. we'll do an example. You'll hopefully see this all come into focus, I guess. All right? Now, we are also going to, go the other way. Okay, we're going to wrap the other way around vertical lines, but let's just knock this out first, right? Or do you want to no, we'll just do this one first. All right, let's take a look at this right here. Let's say that you're given y equals x and y equals square root of x. All right? We're going to do some very basic functions here. The first question I want is to find area of region bounded by these curves. Okay, that's part A, all right? Now, I was going to list out all the different parts, like part A, B, C, all the different questions, but let's just do these one at a time, all right? So let's do that one. What do we do here? Maybe start with a picture? Okay, so we start with a picture. Y equals x. That is a diagonal, isn't it? And then square root of x, that is, well, square root function. Starts here, goes like that, right? Y equals root x. And we can see the region bounded by the two. Okay? So we're talking about trying to find the area right here. What are we going to need to know in order to do this? We need to know where they hit each other, right? So you can try and find these points, and I think they're obvious from the picture. They hit at 0 and at 1, right? Plug 1 into here, you get the same answer. The only other option is to set them equal to one another, right? Let me do that because in my last class we ran into a problem when we did that. I did a different example, but we ran into something, and one of my brighter students in that class said something, and he was incorrect, but it was a good learning lesson. How would you solve this equation? Square both sides, okay, I'm okay with that. Now, anytime you have an equation and you square both sides, you introduce the possibility of extraneous solutions, which means we must check our answers when we're done, okay? Anytime you square both sides of an equation, that can happen. That means you can introduce answers that don't work, okay? All right, now, this is the step. What now?
Could you subtract x from that side to make it like quadratic?
So bring everything over to one side? That is the correct way to do it. The incorrect way to do it is to divide by x, okay? Now, let me show you why, because I know some of you were thinking divide by x. Here's why we don't divide by x. If I divide this by x, what do I get? X, and if I divide this by x, I get 1. Now, is 1 a solution? Yeah, 1 works, right? Put it in here. Remember, we have to check it here. Does 1 work? Yes, it does. But was that the only solution? No. What other solution works? 0. We know that just by looking at it, right? But you don't have, when you divided by x, you lost that answer, didn't you? And the reason you lost it is because when you divide by a variable, you have to, anytime you divide by something, you always have to have a little asterisk next to it saying, I'm going to divide by this, but I promise you it won't be 0. Because if you divide by 0, you have division by 0, right? So in the process of dividing by a variable, you're actually eliminating one of the solutions. So the correct way to do this is to move everything to one side and then factor the left-hand side, x times x minus 1, and then set each factor to 0, and you get your two solutions that way. Okay? So that's just one of those things. I remember I was a student at some point, and I remember when I'd see something like that, I would want to divide by x, but that's very dangerous. So don't ever divide an equation by something that you don't have control over. Like you can divide by 4 on both sides. That doesn't cause any problems. You can divide by any constant you want, except 0. But when it comes to a variable expression, you create issues. I mean, sine x equals cosine x. One way to solve this is to divide both sides by cosine x. If you divide both sides by cosine x, you get sine x over cosine x equals 1, which is tangent x equals 1. And yes, you're going to get some solutions there. That is correct, right? But you've also lost some information here because you've divided by a variable. You've divided by something that you don't have control over, right? You know, what if cosine is 0? You can't divide by cosine x. Oh, okay, all right, we're off. Just be careful, that's all I'm saying. All right, so, all right, we know it's from 0 to 1, right? We know that? Okay, let's go ahead and come up with the formula for the area. What's the area of this going to be? We don't need anything else, right? I mean, I guess we could label this f and this g, right? Because f is the top function, g is the bottom one. So this will just be integral 0 to 1 root of x minus x, that's f minus g, dx, equals dot, dot, dot. So I'm not even going to work it out. And on your next test, your problems are going to look a lot like this. I'm going to give you 2 curves, or possibly 3 different things. You have to find the region. Then I'm going to ask you part A. Give me the integral for the area. Do not evaluate. So that means that's it, box it, you're done, move on. All right? Part B. Find the volume of it wrapped around the x-axis. Volume about the x-axis. Now, if you go and you do your homework for this section, the wording is going to be a little different. So I just want to read to you real quick what this will look like in the homework. It'll say, find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. That's the instructions. I'm just going to say volume about x-axis. Do we understand? Yeah. Okay. All right. Just a lot less to write. Okay, so we're wrapping this around the x-axis. Because it's the x-axis, this is the easier case, right? We don't have to worry about outer radius, inner radius. So I notice here that I can draw a rectangle in here. And I want you to pay attention to something. Because of where we're headed, I want you to pay attention to something. I believe we talked about last class that when we draw a rectangle in here, we just have to be sure that as we move our rectangle from A to B, that we always have the same function on top and bottom, like it never changes. And that does happen here, right? The green curve is always the top of the rectangle and the blue one's always the bottom. Okay? Also, I'm going to point this out again because of what I'm going to say later, that with this method that we've been using to get the volumes, notice that our axis of rotation is like this, right? That's our axis of rotation. And our rectangle is this way, right? And that means that the rectangle that we're using in the axis of rotation are perpendicular to one another, right? Perpendicular. There's another word for perpendicular, it's orthogonal, which is, I prefer to use that word. So have you heard orthogonal? Maybe you have. Orthogonal means perpendicular. It's more mathy though, okay? So notice that with the method we're using, our rectangle is orthogonal to our axis of rotation. Later on today, it won't be. We're going to have a rectangle like this and an axis of rotation like this, and we're going to have a new method on how to do that, all right? Okay, what is the volume? Well, with this, I think I can go straight to the formula, don't you? Okay, I can just go what? Pi, integral, 0 to 1. Top function squared, so it's just x, but I'm going to write it. So that's the top function squared minus the bottom function squared, right? Like that, dx, done, all right? That equals something, but we're not going to evaluate it. In your homework, they want you to evaluate it, all right? And I would do that. I would do that. I would say on the test, I'm going to make you evaluate a few integrals, just to make sure you can take it all the way. But for the most part, 90% of the problems, you're just going to be setting up the integral.
Would you want us to write it like that? Or can we put it as...
X minus x squared?
Yeah, or can we put it as like x minus x squared?
Mm-hmm. Yeah, I'm only showing that because if anyone's sitting here going, like if I just would put x here, someone in here might be like, where did he get x from? Because I squared the top function. Okay? Okay, we ready? Part C. Volume about the y-axis. Now, we didn't talk about this. We didn't talk about this. Will this give us the same volume? Like if we wrap this around the x-axis, we're going to get a volume, right? If we wrap it around the y-axis, do we get the same volume? Not in general. In general, no. Sometimes, if the geometry is just right, it will be the same volume. But generally speaking, you get a different volume depending on which axis you go around. I mean, you can think about it. I'll do it with another example. If I take this object right there and I wrap it around the x-axis, right? It's going to look like, well, I'm not even trying to draw it because you can't really even see it. But it's going to be very long like this, right? Like that. It's going to have a certain volume too. I'm thinking of like one of those like discus, like in the Olympics that they throw.
Oh, yeah.
That's what I'm thinking about, like a disc. It would be like this discus thing, right? And that's going to have a certain volume. If I wrap it around this way though, okay, it's going to look like almost like a bundt cake. I don't know, like, it's bad, right? So it's got like, do y'all see that wrapped around? It's like more like a bundt cake, and I can actually put my hand through it. Oh no, I can't put my hand through it. They come together, sorry. They pinch off at the end, sorry. Right, because that corner comes over here like this. Right, do y'all see the difference in the shapes? Like one is a discus, the other one looks kind of like a weird bundt cake. And if you've even seen a bundt cake before. In general, the volume will not be the same, okay? Certain objects, they would be. What about this one? Remember when we took that curve, we wrapped it around the x-axis, that gave us half the volume of the solid ball? What if I would have wrapped it around the y-axis? That would have got the same thing. It's the symmetry that made that true, all right? So this one may or may not, when we go about the y-axis here, this one may or may not give us the same volume. Let's see. So how am I going to do this one? What do I have to do if I want to go about the y-axis? So it'll still be 0 to 1, but you're looking at y-coordinates now instead, right? So you have to realize that that's 1 still, and that's 0 down here. And then what else do you have to do? You need to take your equations and solve them for x instead of y. So let's do that. Let me solve this one for x. It's done. Okay, so x is y, right? This one, I square both sides, right? I square both sides. Yes?
So if it's like symmetrical about the origin, does that mean that it'll return
If
the
what
same?
is symmetrical about the origin? If
Whatever
the
your function
shape
is. Yeah,
is, the volume will be the same? I don't think so. I don't think so. I'm going to have to look into that a little more. Because I'm thinking of the sine curve. The sine curve is symmetric about the origin. But if you rotate the first arc of sine around the x-axis, you don't get the same volume as if you wrap it around the y-axis. So I don't think that's enough of a condition. Okay, so this one is going to turn into x equals y, and this one's going to turn into x equals y squared. So we have to be paying attention to which one is on, not top and bottom anymore, we're talking about left and right. Right? So now my rectangle goes here, like this. For part C, my rectangle's that way instead. Agreed? Hey, the axis of rotation is orthogonal to the rectangle, right? That's, just pay attention to that right now. Pi, integral, where to where? 0 to 1, okay. Now, which function? Y. Y. This one right here is the one on the right. It's that function squared. So y squared minus the left function, which is the green one, which is going to be y squared squared. I'll write y to the fourth this time, because I think that can only come from one place, y squared squared. And then dy. Okay. Just by comparison, let me go back up to this one. This was x, right? Are we going to get the same numerical answers? Look, when you integrate this, you're going to get 1/2 x squared, 1/3 x squared, right? Subtracting. And you're going to plug in 1 and 0. That's going to give you an answer, right? But when you do this one, you're going to get 1/3 y squared minus 1/5 y to the fifth. And you're going to still be plugging in 1 and 0. And that's going to give you a different answer, because this was what? Like 1/2 and 1/3, right? And this one is going to be 1/3 and 1/5. And it's not going to be the same number. Y'all get that?
Is
Okay.
the bottom one going to be smaller?
Pardon me?
Is the bottom one going to be smaller since it's
I
subtracted?
think, but I don't know. I mean, I haven't thought about it that much. This one right here, this is just going to be 1/2 minus 1/3. That's what that's going to turn out to be. No. No, hold on. 1/3. We'll plug in 1/2 x squared minus. Yeah, 1/2 minus 1/3, then times pi. Right? This one's going to be 1/3 minus 1/5. So this is 5, that's 2/15 pi, and this one is 1/6 pi. So that one's smaller? Yeah. So you get less volume if you go around the y-axis. All right, we good? Okay, now let's do it around something else. So let's take this and let's part D. Let's find the volume about y equals -4. Now, once I start rotating regions around things other than the x and y axis, I like to really take my time with the picture to make sure I've got it, all right? So I'm going to draw this. Continue this down. So -4 is down here. This is my axis of rotation. I'm also leaving some space over here because I'm going to move some stuff to the side. And all right, so my regions now. Let's see, we have y equals x. And then the other one was square root of x.
What about whenever you rotate about an axis like y equals x? Will that change?
Oh, okay. So what if you're doing something that's not horizontal? That's actually beyond the scope of this class. Yeah, it's very problematic. It can be done, but you have to do some kind of strange stuff. Yeah, yeah. You wouldn't do that even like in a Cal 3. I don't remember where I ever ran into that. I mean, it happened at some point, but I think by that time that you would see that you would probably attack it with something different. Like you wouldn't attack it with this method. You would do something different. Okay. All right. So we've got this. We good? Now I'm going to draw my rectangle. Arbitrary rectangle in here. My rectangle is orthogonal to my axis of rotation. Over here, I draw my axis of rotation. I draw my x-axis. I draw my rectangle. This just helps me visualize everything without all the graphs in the way. I'm trying to rotate around this axis, right? So I need an outer radius and an inner radius. My outer radius is the distance from here all the way to here. And my inner radius is distance from here to here.